We'll pick up and continue what I was saying about Bayes estimators last time. And I'm optimistic we can get through the full Cramer-Rao thing. We'll do examples on Monday of how you apply it, but it's basically a formula that you check and you see if your estimators meet a certain criteria. So this is something specific to variances. And so when you're thinking about variances specifically and trying to optimize them, you're probably thinking about the L2 norm. So you might have some bias condition, and you might want to think about, for some level of bias, how do you minimize the variability. So I want to distinguish that from other norms like L1 or 0.1 loss, things like that, that it's not variability per se that you're optimizing, but it's stochasticity in the estimator. So I differentiate those two terms. Variability is one specific form of that. But at the end of the day, all estimators are systematically biased in some way, but it might not be variability that we want to measure, but some other form of uncertainty. And so, Cramer-Rao, I would say, is specific to L2 loss. But those concepts apply to other norms, loss functions that you might look at. And so, unfortunately for those, we don't have convenient formulas like Cramer-Rao. So there's something special about L2. It's a lot of convenience for us mathematically. So I think that's what actually draws people to run after that all the time. So saying that, if you can't do things mathematically and you don't have a mathematical formula, you can always do simulation studies. And so that's always a tool that's in your basket. Okay. Bayes estimators. So here's where we were last time. So Bayes estimator. So I'm going to denote that is E pi. So the pi denotes the prior. Or however you want to think about some weighting on how much you want to put weight on different thetas. It's the same thing. So this is just defined to be the R minimizer over E of the integrated risk. So I'll write down the risk function. That just has E in there. We integrate out X, so the risk function already has that integrated out. Usually I write it down like this, I guess. E down here, and it's a function over theta. And then we're going to be integrating with respect to some weights, d theta. I will point out, here's a fact. If pi theta is proper, what I mean by that is if the prior integrates to 1, d theta is equal to 1, where I'm integrating over all of theta. So sometimes people will just say, a lot of times you can't work out the normalizing constant, and you'll just have the kernel of the prior. So what we mean is that this, whatever this is, if it's just a kernel, integrates to something that's not an infinity. So it's a number, you can write it down. If pi theta is proper, then Bayes estimators are admissible. That's kind of nice. So again, all we're looking at with a Bayes estimator, let's say I have some risk function R theta. For some specific estimator, this is a function over theta. What we're going to use as our criterion is the area under that curve. So how much average risk is there? Bayes estimators optimize that. I'll remind you that Minimax estimators they're different. So they don't minimize the average risk, they minimize the maximal risk. And so that's going to look something like this. So E hat, I'll call it Minimax, is equal to the R minimizer. I'll write it down like this. R minimizer over E of the maximal risk is a function of theta, R E theta. And so that's what Minimax estimators do. I will say a fact about this. Fact, unique Minimax estimators are admissible. The uniqueness just means that if that maximal risk is tied by some other estimator, we might need to check other points of the other estimator and just make sure it doesn't beat it somewhere. So this is basically the uniqueness is just about the ties that can happen. So remember in our definition of admissibility, there's some statement about ties that has to beat it specifically somewhere. And so minimaximality can happen because of just at one point. So if I just draw you a picture over here, I could have some estimator that has some risk function, E theta, and it looks pretty good, except at some point right here. So that risk might be here. This is over theta, where all of a sudden at some little point, the risk jumps up. What's the minimax of this? The maximal risk right here is right there. So bigger at that point. So we have to think about that point. So basically we can just say Minimax estimators are admissible, but we have to be careful about the time of everything. Let me just ask you a question. Is this obvious? So what's the definition of admissibility? Make sure we're thinking about this right. What's that? Yeah. In the estimator, it's just one other estimator out there. If one other estimator out there beats it everywhere, it's not admissible. So a little bit different from that. So you have to be careful with the nuances in these definitions. It's not dominated by some estimator. There's not some estimator that's beating it everywhere in all of theta space. So going to this right here. Is it obvious? Conceptually, I just know this is true when I look at it. I could butter up a proof saying what I understand is true. So what does this say? Bayes' estimator is on average best. So it's bringing down the average area. So if it's on average best, doesn't it have to beat something somewhere? So if my average is lower than everything, then that means at some point in space, it's lower. Think about a contradictory proof, and I'll let you fill in the blanks on this. So sometimes I ask these sort of things on test and see if you can concoct a proof on the fly. So you might want to practice this. Let's do a contradictory proof. My least favorite type of proof because it's not constructive, but maybe it would work in this case. Let's just imagine the Bayes estimator was on average lower than every other estimator out there. And let's assume that it wasn't admissible. That means that the risk curve is dominated by something else. Doesn't that mean that that other thing would have lower on average risk if it's lower? It's never, the other thing is never higher. So, I think so. You can do it with just little numbers. So if I ended up saying, you know, I've got some numbers 1, 2, and 3, I've got some average of those numbers, it's 2. There's some other estimator that's not lower on average, so let's just say it's 3, 3, and 3 are the different points for theta. on average that's 3, but I'm going to say that that dominates the other thing. No, that's not true. That's not possible. And so it's higher everywhere, at least it ties at that 3 point. And so it's not dominating. It can't have a lower average. You could concoct a real proof of that. These proofs are easy to find online. I'd recommend you look at those. So they're 1 or 2 line proofs. Okay. So that's kind of a nice thing. So if you're a Bayesian and you're using proper priors, then you have an automatic way of saying that my estimator beats you somewhere. Whatever estimator you're using. So you could maybe tie. So if you're using my same estimator. And so I think this is the thing that turned a lot of Bayesians into Bayesians. So you could do this automatically. I'll say another fact. And you can see if you can prove this. This is easily available to find online. Bayes estimators with constant risk are Minimax. So it goes through the maximal risk point right here. This estimator right here doesn't have constant risk, it jumps up at a point. So that's not constant. So what's an example of a Bayes estimator with a constant risk? I like to think through examples when I construct proofs. What's an example of an estimator with constant risk? Doesn't matter how I derived it. Think about your simplest examples out there, the distributions we always go running to. There's uniform, that's one of them. That's not the one I'm looking for. What's the other distribution we always go running to? Normal. So if we're estimating mu from a normal distribution, what would you pick for your estimate of mu? X bar. What's the bias? What's the variance? Isn't that constant? It's a function of mu. So that's constant right there. So that's at least, if I'm working through the L2 norm, there's an estimator with constant risk. So we have to define our loss function. So L2, is there any way I could derive X bar as a Bayesian? What prior would I have to use? Which one? Yeah, the flat one. So it's not the normal prior, but the flat prior is a limit of that conjugate prior. So if you take your conjugate prior and you blow the variance out to infinity, it'll make that flat, so that means you're using the constant prior. So it has constant risk. Does this theorem apply to that? No, because the flat prior is not a proper prior, but it is admissible because it is Minimax, and we can prove that as well. And so we can't apply that theorem to that per se, but X bar is a Minimax estimator. It's also a Bayes estimator, and so we don't have admissibility because of this, but we have admissibility because of this thing right here. It's Minimax, and Minimax estimators are admissible. So sometimes you have to layer these things together in different ways to claim admissibility. But if I gave you a proper prior, the normal conjugate prior with a finite variance, you're going to beat something somewhere. And it's probably going to be around where you've centered that problem. You're going to do a really good job over there. Let me ask you a question about that same example. If I pick my estimator to be mu hat is equal to 7, is that estimator admissible? So 7, if I just say, no, my answer's 7, get out of my office. So You're like, I've got all this data, let me tell you about my study, I want to know mu and the normal distribution, 7. So I don't want to hear any of your stuff. So, is that an admissible estimator? If mu is 7.
Oh yeah, if mu is 7.
Yeah, so we didn't even look at X bar. So if mu is 7, maybe around that. So it is admissible. So admissibility on its own is not necessarily something we just need. We can get it for free. So that's what I kind of think. A lot of these definitions are a little bit on the weak side. If you're a mathematician and that's all you're thinking about, maybe this is good enough for you. But I can always get admissibility. And so I can operate as a Bayesian and get admissibility by using proper priors, and I can get admissibility just by picking a constant for your estimator as well. If I think about what the risk function is for X bar, constant, this is sigma squared over n. In my risk function for the constant estimator 7, so this would be for mu hat is equal to X bar. This would be for mu hat is equal to 7. That's my risk function. This is over mu. This is beating it over here. So it's admissible. And it's going to be really hard to beat it right there because you can't drag a risk any lower than 0. So I just want to point out all these definitions. They're a little bit weak. This is sometimes called the least desirable Minimax estimator, the one with constant risk. You might like it because it has constant risk. But if I could find a Minimax estimator that does something like this, right here, that is bounded by that. So this is just going to be some other estimator. Other Minimax estimator. You can prove that X bar is Minimax. So I will just point that out. This is Minimax. We'll see if we can prove that. My assumption in all of this is my loss function is L2. So this would be Minimax too because it has the same maximal risk as this. So, except this one is now beating that everywhere else. Question is can you find that estimator right there? Could you construct it? But this one right here would be Minimax, and it would be beating that thing right there. They're both Minimax. But this one's clearly better because it goes lower somewhere else. So having a flat risk function isn't always desirable. If you can bring it down in other places, you'd like to do it. So I tend to think Minimaxality is a pretty easy thing to get. All I have to do is get my risk functions from my Bayes estimator, wiggle around those knobs in the prior, and flatten out that risk curve. And we did that for the beta binomial example. So saying that, because you can operate as a Bayesian and come up with all these different estimators, I think that did compel a lot of people to become Bayesians back in the 80s. So that's my historical recollection. So I talked to Jim Berger about this, and he said I used to be a frequentist, you know? And so what I think he means is not a Bayesian. So unfortunately, we're using the term that way. Bayesians can be frequentists. So, but it was all the decision stuff that provoked them to be a Bayesian. In the 60s, Bayesians tried to compel you a different way by talking about subjective probabilities, and you have your own personal inferences, and you can condition on information that you want to. And they would show this conditionality argument, and they would say that the subjective nature of the Bayesian estimators is compelling, and that's why you should want one. And I think a lot of people didn't like that. So that they're like, that seems a little bit flaky. You know, I have to tell people, well, it's because of my opinion, you know? And so I don't think that's a bad answer. I'm a subjectivist myself, so long as you can back things up and say why you pick certain criteria. I think those are good answers. I tend to think that these objective answers where we're optimizing something, they're also subjective because we've had to pick the optimality condition. So for instance, maybe the loss function. So there's no theory that's going to tell you you should pick this particular loss function. That's always a subjective question. So lots to think about. So Bayes estimators can subsume these right here. So there's connections between all of this. Let's just pick up where we were last time, that we ended up showing by writing out the risk function. The risk function is just the integral of the loss function where I'm integrating across the data space. I'm weighting this one as well, but I'm weighting it by something that we already conceptualized as important, the sampling distribution. So given a particular theta, I can see on average how many losses I've incurred. And so we rewrote this in terms of the double integral. I put that in. I applied Fubini's theorem. I multiplied and divided by the margin of the data. And I ended up coming up with, this is equivalent to optimizing the R minimizer of the posterior losses. So we'll just write down our loss function E of x theta, pi theta given x, d theta. So they're equivalent to each other. I could have written down the other integral right here and then made it exactly equal to this thing right here, where I'm going to integrate over the margin of the data. So that would go right here, and then I would have a dx term. And that's where I applied Fubini's theorem. So we rearranged everything and showed that this double integral was that double integral, and the interior integral was just this one. And this is the only thing that depends on E itself. So it's the only place where E appears in this. And so I'm conditioning on a data set so I can just ignore that right here. I kind of like this because it gives me a direct way of applying this in practice. Given I've got data, how do I construct my estimator? And so this is a conditional argument right here. So this is the posterior expected losses, and that's what you're minimizing. And that's what the Bayesian estimator is. So that's kind of convenient. So it gives you an operating technique. Write down the posterior, optimize your loss function. And that's what the Bayes estimator does. I kind of like that. So I didn't say if you use an improper prior, you don't have admissibility. You could. There's just no guarantee right away. You don't have a theorem for that. And it's kind of nice to have some of these theorems because it's just automatic for you. You don't have to go out and check over all other estimators or come up with some specific theory for your particular estimator and show that it beats everything else. That can be a near impossible game. There are advantages to not coming up with optimal estimators if you're an academic. It means that if you find something better, you get another paper to write. I don't think that that's a very good objective function. So if that is your objective function and you've encoded that into your losses, you should probably tell people. So saying that, all the scientists that I've ever met, and I've tried to convince them with all of this stuff what to do, they seem to be of the notion that their utility is based off of whether or not their paper gets published and their grant gets funded. So I do understand the practical constraints, but maybe we can encode a little bit more science into our problems. So, okay. Let's look at an example. For L2 expected value of theta given x, posterior mean, is optimal. So it's our Bayes estimator. So keep in mind, that's true regardless of which prior you're picking. And so it's optimal in some sense with respect to how you weighted things. I like those knobs and widgets that I can say these values of theta are important and these ones are not. So these are plausible or not. When I talk to scientists and engineers and I work with them on problems, they're usually able to tell me stuff about that. And they'll have strong opinions about, no, this parameter cannot be negative. Things of that nature. So that happens all the time. Okay, let's just prove this. This is pretty quick. E pi, and again, the assumption is L2 loss. This is just going to be the arg minimizer over E of the integral of my loss function well, I guess we've already got our loss function, so I'll just write it in one step. Ex minus theta squared, and then I got my posterior distribution. So we've spent a little bit of time calculating some posterior distributions under different types of priors. If you want more practice on that, take a full-blown Bayesian class. We'll tell you all kinds of properties of various priors and which priors you might want to choose in different applications. We can do this. This is a calculus problem. Everything is smooth, so that's kind of nice. So what we might do is we might take our derivative with respect to our estimator. This is my conditional estimator, my estimate when I plug in actual data. So that's where I'm taking my derivative, and I'm going to integrate this function minus theta squared pi theta given x d theta. And so this is going to be 2. I'll just factorize out my 2 ex minus theta pi theta given x dx d theta. So as soon as I set this equal to 0, I need to do something and at least to note that that's my estimator. We don't really need to do it here because we've already called it an estimator. So that little hat, if I throw it on in that step, if you're an autopilot and as soon as you set things equal to 0, you feel like throwing on the hat, it's already there really. So this wasn't the truth. I didn't integrate over theta. Or I didn't differentiate over theta. I differentiated over the estimator and already called it my estimator. And so I can just set this thing equal to 0, get rid of the 2, that didn't do anything, and then I can factorize this out. This is all linear now in terms of that, and I can just write down, I'll write it up here. Bless you. From this, I can just write down that the integral of E x pi theta given x d theta is equal to integral theta pi theta given x over theta. And I'm integrating over all of theta. So I guess I normally write that down is omega theta. This doesn't have anything to do, theta doesn't appear there. I shouldn't say it doesn't have anything to do with theta. There's just no theta parameter in there. It's supposed to be estimating theta. But there is no explicit theta as a function of the data. So I can factorize that out, and I'm just left with Ex integral pi theta given x. Bayesians are always working on a probability scale. If you don't have a proper posterior, your analysis is worthless. If you use improper posteriors, you're no Bayesian. So you're not thinking on a probability scale. And so this thing right here is 1, right here, and this is just equal to, so I'll get rid of that. This Ex is equal to that. This thing, what is that? That's the posterior by definition. I will say, I've seen this before on QEs when I ask about the median. So for L1 loss, we're going to have something like this. EX minus theta pi theta given X. I'll let you work through how to do this problem, but if you touch this with a derivative, I'm giving you a 0 on it. So if you try to differentiate the absolute value sign, and I do not care if you do this. So if you end up doing something like, oh, I'm going to integrate theta from, I'm going to integrate where this thing is going to be positive. So I'm going to integrate maybe from, my estimator is going to go from, I don't know, something like this. It's going to go from d theta will go from 0 to EX, something like this, and I plug in the integrand. I'll plug it in like this. EX, I'll write down theta minus EX. Pi theta given X d theta plus integral from EX, I'll say from EX off to infinity or something like this. And I've seen these sort of arguments that people try to concoct where they're like, I'm just going to write this thing down and write it without the expected value. And this is obviously all butchered already with the bounds. But I see people muck around with these bounds right here and try to write this thing out and try to make this thing positive right there and that thing positive. And they're like, oh, I've taken out the absolute value sign. I'm going to differentiate over it now and everything should be good. It doesn't matter. You cannot differentiate over that. So that's really my point. So I'm not saying this can't lead to a good argument by changing the bounds and breaking it into two pieces, but I am saying that as soon as you touch it with a derivative, I don't care how you've written it out, how you've remanipulated it, you can't differentiate that function. So this is non-differentiable. I'm going to refer you to a problem in the book that will show you how to solve this. Problem 713 in Casella and Berger. And the solution to this is in the solution manual. This will show you how to do the right analysis to find the optimal answer to this. And I'll have you work through that. It's not specific to this problem, but all the math you would do in that problem is exactly the same as the math you would do for this problem. The answer to this is the posterior median. So how do I get the posterior median? It's not too hard. So the posterior median is just solved by integrating pi theta x. And I'm going to go from negative infinity to some point right here. And I'm going to integrate over theta. So I'm going from the left-hand side. I'm accumulating mass, and I want to do this until it adds up to a half. So that's what the posterior median is. So I've got half of the mass is the point that you've added together half the mass. For 0, 1 loss, and I'll let you think about this as well. E pi is the posterior mode. You probably want to think about that in discrete cases when we use 0, 1 loss, but this would be true for even a continuum. And so this is pretty conceptually obvious, but you probably need to draw yourself the right picture to think your way through it. A lot of people call this the map estimator, and we talked about that back in the simulation assignment. So the map is the maximum a posteriori estimate, it's the posterior mode. They're synonyms. So all things you can think about. So operationally, getting a Bayes estimator is not that difficult if you have a posterior distribution. If you have some really weird norm, you probably have to do something computational to work through these intervals. So all kinds of good stuff we can say about various estimators. And I know we're going fast through this, so we'll kind of circle back around and talk about this more in the context of examples in the next few lectures. Let me show you something new. This is the Cramer route lower bound. So Tukey's, I'm sure you guys know who Tukey is. So everybody talks about him. So he's one of my top 3 statisticians out there. I like how he gives us practical tools. I also like his intellectual prowess as well. I also like him as an individual. He passed away a long time ago. I was in college when he passed away. But if you read history on Tukey, you probably like him too. He says, it doesn't matter how you come up with your estimator. I hate this whole Bayesian, non-Bayesian game. I don't even want to talk about it. Why people argue about this stuff. I don't care how you come up with an estimator. All I care is how you evaluate the estimator. So that's all for you, how you think about it. If you want to be a Bayesian and derive something, if you want to be something else, all that matters is how you compare various estimators. I half agree with them. I also agree that in my own daily life, I want to know how to think about things, you know, so that I can develop things. And I have at least a starting point on how to get somewhere. I choose to operate a particular way, but there's other ways to operate out there. So Cramer route is not specific to how you got your estimator at all. It's just specific to thinking about the performance of the estimator. And so I'll say this applies directly to L2 losses. I wish we had these for every loss function out there, and if you could come up with one of these for like L1 or something like that, you would be famous. So it will remember your name in 100 years from now. It'd be famous. Usually we're left with simulation studies for hard forms. But this is an oldie but a goodie. It says this. So if I have x's, they're coming from some sampling distribution. I goes from 1 to n. This isn't specific to an IID distribution, so this could have some conditioning in here. There is an IID form of this, and we'll talk about it on Monday. And so we'll derive this in the IID form as immediate consequence of what we're going to derive right now. We'll look at some examples soon. So consider an estimator. The estimator WX. So where that's just all my data. The Cramer route lower bound says something, but you need to check a couple conditions first. So I'm going to write those up front so you remember to check these conditions. It's very likely to give you problems where these conditions do not apply, and I'll ask you what Cramer route says about a particular estimator. And these conditions don't apply, and what you're supposed to say is nothing. But I've seen people waste a half hour of math, you know, going through things and then saying, here's the Cramer route lower bound, blah, 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 blah. And that's just too bad because it really said nothing from the get-go and you shouldn't even be calculating it. So always check these conditions. So our conditions are the derivative of EX, EWX, is equal to the integral of the derivative. So I'm assuming x is living in a continuum. When I write down integral, if you want to change this to a summation sign in the discrete case, everything lends itself over to that example. So I haven't defined exactly what my integral means. So this is meant to be general. The derivative of wx f of x given theta dx. I'm going to integrate over all of x when I do that. So that's one of the conditions. This is almost obviously true in a lot of cases. All we're doing, keep in mind, the integral over that stuff is just the definition of expectation. So all we're saying is that we can bring the derivative inside the expectation operator. So that would be equivalent to just bringing it in right here. So that's a statement about Fubini's, that you can interchange the order of differentiation and integration. So you might think of Fubini's as a statement about interchanging the order of integration, but derivatives are the inverse operator for integrals. So this would apply to derivatives as well. So this is just Fubini's applies. An example of something where Fubini's does not apply would be if I had theta on the boundary of the space. You wouldn't be able to drag that derivative across the integral. So that uniform zero theta example, Fubini's doesn't apply. We can't use Cramer-Rao to say what's best. But in problems where you can apply Fubini's, Cramer-Rao will apply. There's only one other condition, and it just says that the variance of Wx is less than infinity, greater than infinity. That's a good one. Less than infinity. That's just saying that it exists. So the thing we're trying to talk about and derive a bound for exists in the first place. Okay. Here's the statement. This is the Cramer-Rao lower bound. It's a bound on variances. This is going to be greater or equal to, so it's going to be bounded by this. This is how far you can shrink this variance right here. This will be dp theta, expectation of Wx. This is squared, divided by the expectation of the derivative of the log. Since I'm taking a derivative of this function, I usually say likelihood, but we're kind of using this function in both contexts because my expectation is going to be over x right here. So this is x given theta, this is x given theta. But this will be squared right here. That's the end of it. So this is a true statement, so long as these two things apply. I want to point out this is just a formula that you just plug things into. So if I'm asking you, what's the Cramer-Rao lower bound? You're just doing these two expectations. I want to point out that if Wx is unbiased, right here, then expectation of Wx is equal to theta if Wx unbiased. This function down in the denominator is called the Fisher information. There are other ways you can write this where you don't have to work with this quadratic, and we'll examine that on Monday. So I sometimes apply a formula that involves two second derivatives, or a second derivative. I kind of like that second derivative because it sometimes makes the math easier, where this quadratic sometimes makes the math harder. So we'll explore that. The formula that I'll give you, the condition whether or not it works, is this exact same condition. It's whether or not Fubini's applies. So if you do know the negative expected value of two derivatives of a log likelihood is also the Fisher info, I kind of like thinking about that sometimes. That applies if food beans holds. We'll look at that on Monday. Let's prove this, or at least start a proof. I'm going to fill in probably the part of this that most people get confused about. So I want to look at some estimator, or I'm going to say just some function. Some function g of x, expected value of this thing, and I'm going to take a derivative over it. What the book does is they call this wx all the way through the proof, but then they make a substitution for wx. They say wx is wx and we'll apply it and derive this formula, but they make this quick turn in the proof where they say, consider when wx is equal to 1. And for some reason that just wildly confuses people. So I'm going to change the notation. I'm going to say some arbitrary g of x, and then we're going to apply this formula to two different forms of g of x. So later, we'll examine two cases. Examine g of x is equal to 1, and g of x is equal to wx. So I'm just going to write down some facts, some mathematical facts, and we'll recycle those facts. So I'll let g of x be wx eventually, and that will apply specifically to this. And then at some point I'll make g of x 1. Probably do that in 2 minutes. So let me just write out what this thing is. So this is just the integral of d theta gx f of x given theta dx. Right there. That's the definition. I erased our condition, but our condition is we can drag this thing inside. Keep in mind, g of x is not theta, it doesn't have a theta on there. Has something maybe to do with theta if I'm using it as an estimator, but I can drag this thing inside. And I'm going to just drag it right here, d theta. Right there. So I can do that because of condition 1 that has to apply. Fubini's holds, g of x doesn't have the thetas in there. This is going to be the integral of gx derivative of this function. As soon as I start operating on theta, I always think of it as likelihood. If I integrate over x, then I think of it as a sampling function. So I'm going to rewrite this just a little bit, and I'm going to multiply by some funny form of 1. I haven't changed anything. So this thing is just the expected value of gx derivative d theta fx given theta over fx given theta. So this is just the expected value of all this stuff where I'm integrating with respect to that. That's just all the stuff that's in there. So I'm going to rewrite this. Is this expected value of the derivative d theta, let me rewrite it a little bit different, g of x derivative over theta of the logarithm of f of x given theta. Those are all the same things. So the derivative of log theta, it's 1 over whatever that is. That's down here. And then I apply the chain rule, and that's there. So I've just written this a little bit differently. It's all the same stuff. Keep in mind, my assumption has to hold for this to be true. So I'm going to substitute g at x is equal to 1 in all of this. This is the part that people get a little bit confused. They're like, well, when do I take my estimator to be 1? They're just recycling notation in the book. I'll make it explicit by just coming up with a different notation. So what we just proved, if I take g of x is equal to 1, is an identity that people use pretty regularly. So this says the expected value, so for g of x is equal to 1, the expected value of 1, derivative d theta, is equal to the expected value of the derivative of the log, and I say likelihood here. I just plugged in a 1 here. I went over here and I plugged in a 1 right there. Left-hand side is equal to the right-hand side, so I have that. Somebody help me out. What is this? 0. Expected value of 1 is 1. Derivative of 1 is 0. So all we've said is this is 0. This is an identity that we use all the time. So when I see somebody write this down, I think 0. But I'm careful to remember Fubini's has to apply for that to be true. We're going to recycle that 2 times in this proof. So what the book does is they slide this little proof in the middle by changing what WF is. They expect you to hold on for that ride. This is true. We can just take this as a fact. We'll use that next time. There's one more fact that I want you to be aware of. And we can roughly prove this next time. This is true for any 2 random variables. The covariance squared is less than or equal to the variance of x and the variance times the variance of y. This is, in statistics, people will call this the Cauchy-Schwarz inequality. You will see this applied to vectors in linear algebra. It really is the same identity. This is Cauchy-Schwarz. Can somebody tell me real quickly why this is true? Maybe not. Think about the definition of correlation. Yeah, exactly. If I take the square root of everything and I divide these down, that's the definition of the correlation coefficient, and we know that lives between -1 and 1, so proof complete. Here's what we're going to do next time, is I'm going to take x, I'm going to redefine it as wx, sorry for recycling my notation, and I'm going to take y is equal to the derivative of the log likelihood function. As soon as I plug these things in and apply this twice, I will have the Cramer-Rao lower bound. So it really is like a 3-line proof. That was Cramer-Rao's, so as Rao was studying at Penn State and came up with all of this. And so, and that was his thesis, 3-line proof. Obviously he said a little bit more along the way, but that was the nitty-gritty of it all. We'll finish that proof next time. Do a few examples. So sorry for running over. Happy Friday to you guys. We'll come back around to this, look at some examples. Remember, we have a midterm on Wednesday. What I'll probably ask you to do on the midterm is not do the proof, but I'll probably just ask you to do things to meet the Cramer-Rao lower bound. So I'll give you a hint, like x bar in the L2 norm meets the Cramer-Rao lower bound. So the Cramer-Rao lower bound is sigma squared over n for that case. So no surprise. Try to work that out, just to give yourself a little bit of experience over the weekend. That's it for that one. Thanks.